This is the work of an Italian startup based in Milan, who I supported by providing my past work and literature work on biochar. So they wanted me to speak because maybe in a scientific meeting I can explain their activities better. So their project name is LWARE, Leather Waste Rebirth. We are speaking about leather wastes from footwear, clothing, leather goods manufacturing processes. These are pre-consumer products, which are waste and can be and have a cost for the company who generates them, and also an environmental impact, especially given that foreign countries like China have stopped to import from Europe waste, and this has to be disposed in landfill and incineration system now. We have in Italy 2.4 million square meter per year of leather waste that come, as I said, from clothing industry. More of this waste can come from automotive sector or furniture sector, but this is not the scope of this project. The transformation of leather can be applied to generate activated carbon, so giving an added value to this waste. The process is a circular one, where we produce activated carbon from the waste, and we use it for filtering wastewaters. And in the same time, we separate the active carbon from heavy metals, and through a process which was patented by this Phoenix Italy company. And in this way, we close our cycle. Activated carbon from leather waste has we find a particular application, which is the filtering of micropollutants, and in particular PFAS. PFAS are very problematic emissions into the water because they are let's say forever chemicals. They cannot be degraded, so they are a very big environmental issue. So as I said, what I did with this company is to provide my work, which was done previously to the current Marie Curie work, while my Marie Curie work is on bioenergy with carbon capture and storage. Before I worked on pyrolysis, biochar production, and we see here from lignin pyrolysis, for example, or lignin conversion, which kind of goods we can produce. And we see that activated carbons are listed here, and they are added value products. So the production of activated carbon is interesting both from biomass and waste. My previous experience was also in collaboration with Lignocost. We did an exchange in UK biochar, in fact, in the production of activated carbon from lignin. So we try to link all these activities. And also my previous group in University of Perugia is producing activated carbon to filter, let's say, wastewaters from olive mills in another project. When we talk about activation, just to make an example of a plant, This is physical activation in a rotary kiln using steam, which is produced in part, at least, from the pyrolysis volatiles, which are burned into a boiler. In my opinion, I show this process because it's the most convenient one. It is a physical activation, while in chemical activation we should use chemicals, and this could have an impact also on the let's say process, on the plant, and also on the environment. In fact, we see here that we have a physical and chemical activation, and we could have a pretreatment, which is ATC, HTC, or pyrolysis, or the raw materials can go directly into the activation phase. From here, we see that activation is a complicated step, many choices involved. And from these choices, we can influence the final carbon properties. We can influence the carbon properties, the structure of the activated carbon, which here we see is made by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 13 types of organic carbon groups, like alcohols and whatever. We can understand that these different groups have different capacity of releasing hydrogen, and so they have a different pH of the char. And if we want to use the char as an adsorbent, obviously we have to decide how to make an engineering of this carbon, because it depending on the process we use, the pH of the carbon we obtain can be very different. The pH, which I think is the most important characteristic for an absorbent, is also influenced by the ashes. So before designing our final product, these were the two parameters we had to consider very well. Here is why the pH is important in the activated carbon for using it as an adsorbent. And we know that the key parameter is the point of zero charge, so which is defined by the pH for which the net surface charge of the adsorbent is equal to 0. If the pH is below the point of zero charge, we will absorb anions. If it's above, we will absorb cations. This depends also on the pH of the wastewaters that we are going to treat. So in our case, as we will see in the future slides, the pH was alkaline. So our problem was how to produce an alkaline biochar. And we know that if we increase the temperature of pyrolysis, it's very probable that our alkalinity will increase due to the alkali metals contained in the ashes, let's say so. So first step to produce an alkaline material was to increase the pyrolysis temperature. We know also that there are different mechanisms for absorbing materials, not only chemical absorption, but also coprecipitation, complexation, ion exchange, and physical absorption. So once again, the techniques to produce activated carbon and or modified biochar are multiple. What we did is an activation at 750 degrees C, heating rate of 20 degrees C, duration 1 hour, flow 200 millimeter, and carbon COH charcoal ratio of 1:1 or 1:2. The mixing between COH and charcoal, which in this case we used chemical activation because in the lab was more direct, was through ball milling, then washing, neutralization, because we loaded our biochar with a basic compound, and then washing and filtering again the final product. All these processes were performed by a contractor who was the laboratory of Professor Alessandro Bartocci in Padua University. This was equipped with a drop-down furnace and drop tube furnace. And it was very nice because he was very expert on BET analysis applied to ceramic materials, but in this case, he applied his techniques to biochar. So here we see, for example, the final BET of our product, which was performed at 300 degrees C for 12 hours. The isotherm we obtained was H4 type, and it's composed by two isotherms, type 1 and type 2. The high absorption low level P2, P0 is due to the filling of the micropore fraction, while the lower limit of the absorption curve is in P2, P0, and this part of the curve is mainly explained by meso and microporosity. Final BET analysis was 1,864 square meters per gram, and with a correlation coefficient of 0.99. We further analyzed the distribution of the porosity with the equation of BJH and DFT analysis for the microporosity. And so from our final results, we obtained that the final diameter of the pores was on average 8.5 angstrom, but also dimensions of 4.3 angstrom and 13.0 angstrom were present. So the carbon had a good BET and also a good ratio of microporosity. On the other hand, still traces of metals were present. So further research will be applying the patented processes of Phoenix to this material to reduce even more the presence of metals. And these are the SEM analysis. Here we see at different zooming dimensions, and also here we see that the presence of carbon, oxygen is prevalent, and then surely we have some metals that we have still to reduce. The final product was tested in the framework of the Lombardy Energy Clean Tech cluster, which is called LE2C. This energy cluster sees the Milan Polytechnic University as a partner, and also the company Phoenix is inserted into this cluster. Together with the waste treatment plant, which is named L'Ariana Depot. The cluster has a work group on micropollutants, which are a very hot topic of research, obviously. And inside this work group, it was developed a project named Experimental Development of Technological Strategies for the Reduction of the Presence of PFAS in Wastewater and Sludge. Inside this project, we performed let's say a round-robin test, we can name it, in which we have compared different activated carbons. Here is our, and is indicated in green, and we can see that the performance of our activated carbon in terms of reduction with a concentration of PFAS of 50 milligrams per liter, and the reduction is indicated in percentage, is comparable to other activated carbons, with the advantage that in this case, the cost of this activated carbon could be reduced by using a waste. Here we see that the tests have not been performed for only one PFAS, but we took into consideration many different components. These tests were performed by Professor Manuela Antonelli and engineer Beatrice Cantoni at the Department of Civil and Environmental Engineering in Milan Polytechnic University. So I finished my explanation a little with some time early, and for any question you can contact info@phoenixitaly.it and visit the website. And as I said, I helped only consulting literature, so for free, just because I'm very passionate about biochar applications and biomass energy.
Thank you very much, Pietro, for your presentation. Really interesting. And now the option for questions. So if anyone has a question, please write into the chat or just unmute yourself. That's also a possibility. So my question was, what I didn't really get is, Phoenix wants to physically activate, or is it chemical activation now?
Yeah, you know, in my opinion, what we could do in the laboratory, let's say that this research was conducted with a small budget also. So what we could do fast to obtain a very high porosity was chemical activation, but and also more standardized. But speaking with other colleagues, what we encountered is that the washing process, if you do chemical activation, has some criticalities, because it's very difficult to completely neutralize your product. At least this is what we have found. And also, you know, a big issue that I did not have the time to explain is the yield of product. Because, for example, if you put the biomass directly into the activation process, maybe you have less losses. In this way, making a two-step process, you have more losses, and usually the yield of pyrolysis is 1/3. The yield of activation could be 50%, let's say so. If you go to wash and neutralize many times, because maybe you have to do this many times, you decrease further your yield of a great amount, I think. So what I see more feasible for scale up of the technology is surely a physical activation, because also, as I said, this is a kind of gasification. So in this way, you can recover the gases and recycle it to provide energy to the process, and it would be very nice. I don't know if this can be done in one step or two steps, but this is really an interesting topic, I think, to make further research.
Okay, thank you. There are now some questions. So the first one from Ted Silberstein. Does increased heat cause the reduced structure surface area of biochar?
Does increased heat cause the reduced structure surface area of biochar? Yeah, maybe this is on the slide where we saw the alkalinity, maybe. Yeah, sure. Yeah, sure. The increased heat increases the surface area for sure. But if we are talking about pyrolysis, I think that ranging from 400 to 700 or 800, we cannot increase too much the surface area. I think we can arrive to 40, 100 maximum square meters. So we can really not achieve activation with a normal pyrolysis. This is why we can choose to use a chemical for activation, and the advantage of the chemical is that we can operate at 500, maybe 600 degrees, while if we go with the physical activation, I think we have to reach much more higher temperatures, like 800 at least. And obviously this has an influence on the energy costs of the system. This is very interesting to see. I don't think that steam gasification, because this activation is steam gasification, could be an autothermal process. I think it's very probable that you have to sustain the process, and yes, maybe recycle these gases for steam production, maybe recycle some also for heat production or preheating. But the heat integration in these plants is also a very interesting topic. What we learned also with what I learned from this company, because they communicated to me, is that the market of the activated carbon is done by very big plants, so on a very large scale. It's very difficult to have them. For example, I don't think there are in Italy. In Italy, there are only regeneration plants. So maybe also to produce a very niche product on a small scale, I think maybe it could be an interesting option. Also because this market is growing very fast.
Yes. So if you're interested in this in an integrated activation system, you can look at Energy Plus, I think they're called, from Singapore. They have a coupled pyrolysis activation reactor, just because they visited us a couple of weeks ago. So if anyone wants to take a look.
Energy Plus.
Yeah, with an A at the beginning, not an E.
Okay, energy.
Yeah. So the next, I can send you an email after.
Thank you.
The other question from Magdalena was the activated carbon somehow pre-treated before the adsorption tests, perhaps agglomerated?
Yeah, this is a good question, because one issue we had in these tests was the sides of the carbon. As you saw before, we used to mix the carbon and you can mix carbon and potassium hydroxide in different ways. We did this with ball milling, because usually if you make a solution with this potassium hydroxide, it could generate vapors or let's say have something that damages the operator in the lab, let's say so. So we did this with ball milling, and with ball milling, obviously we had a very fine particles. This was not wanted by the laboratory which was involved in the analysis of PFAS. So to increase the dimensions, my suggestion could be to use the size we obtained from pyrolysis, let's say so, and absorb the chemical into the biochar, making a solution. So changing from ball milling to another system of absorption, because another research in which I was very passionate was pelletizing and aggregating charcoal, but this is really not so easy. So instead of pelletizing as a post-process, I would prefer to start with the size which is bigger.
Good that you say that, because Magdalena is a specialist in pelletization. So the last question.
Yeah, I remember that from this pelletizer was exiting a black cloud which was diffused in all the laboratory.
Yeah. So you can also contact Magdalena if you want to work with her. She's an expert there to avoid the black clouds. So yeah, the last question before we go to the second speaker is from Nadav. Can you say how do you change the reaction pH at an industrial scale, and also the activated carbon production from the lab scale?
Yeah, we based our, this is a trade-off. So this was a particularly different process, because we came from waste. But on the other hand, we can think that many people produce activated carbon from coal, and maybe they have the same problem. So the first parameter is the ashes. It's very probable that if you maintain all the ashes inside the biomass, especially if we speak about biomass or organic carbon, let's say so, it's very probable that it has a high content of alkali metals. So if you concentrate these alkali metals, it is sure you can already achieve a pH of, or a point of zero charge of around 8 to 10 quite easily. Then there is another factor that chemical activation can be performed either with a basic compound, NaOH, KOH, or an acid. Given that we wanted basic, very high point of zero charge, we choose to activate with a basic compound, and I think that this influenced our final quality. Then, as I said, we have to neutralize this. It's very probable that if you neutralize this compound, the basic and the acid you use to neutralize will form a salt that will go away with the water. If the washing is not too harsh, we manage to have a very high pH. In some sense, we have loaded a little the activated carbon with the basic compound.